In Chapter 7, we will be looking at three major types of reactions. The first type of reaction we're looking at is called a precipitation reaction, and here in video 7.3 we'll look specifically at precipitation reactions and solubility rules. The major characteristic of a precipitation reaction is shown here. A precipitation reaction is when two aqueous ionic compounds combine as reactants to form a solid as a product. This solid is insoluble in water, and the solid is called a precipitate. Now, precipitation reactions follow what are called solubility rules. The solubility rules tell us if a product that can be formed from a precipitation reaction is going to be aqueous or solid. In other words, it tells us if the product will be soluble in water or insoluble in water. And so we'll look next at the solubility rules to be able to make these predictions. And I want to just summarize what we'll look at here. For reactions in water, if we have that AQ state of matter designation, that means that it is soluble in water. And it dissolves in water. Ionic compounds show their solubility by dissociating into ions. However, if we have something that is solid in a reaction in water, then that means that that compound is insoluble in water. Meaning, even if we put it in water, it remains a solid because it just does not dissolve. This compound lead to bromide is insoluble in water. So if we did this reaction, we would see two aqueous solutions combining to form a solid. Now let's look at solubility rules. Solubility rules help to predict if a solid will form. Solubility guidelines are outlined here in table 7.2 from your textbook. So it's very important to have an understanding of what makes a compound soluble or insoluble, and to look at a compound and be able to predict if it's soluble and will have an AQ designation, or if it's insoluble and will have a solid or S designation. The solubility rules are related to the lattice energy for ionic compounds. Remember that lattice energy is the strength with which two ions are held together in an ionic compound. The higher the lattice energy of a compound, the less soluble it is in water. And the lower the lattice energy of a compound, the more soluble it is in water. Now in this table, we're looking on the top here at soluble compounds. On the left and on the right here is common exceptions. In the bottom we have insoluble compounds and common exceptions. I want to focus the attention first here on the top for soluble compounds. Compounds that are soluble will be made up of ionic compounds that are made up of ions that when they form an ionic compound tend to have low lattice energies. This means that the ions are either really big or they have single charges, or a combination of the two. Looking at our soluble compounds, the group 1A cations, lithium, sodium, potassium, rubidium, and cesium, and also ammonium, are ions that are soluble with no exception. This means that any compound that contains one of these ions will always have that aqueous state of matter designation after the compound, meaning that that compound will always dissociate into its ions. Other ions that are always soluble are nitrate, perchlorate, and acetate. Any compound with these ions will also always be aqueous. Some compounds that are aqueous most of the time, but do have exceptions to their solubility, are here. Here we have chloride, bromide, and iodide, also called halide ions. These compounds are always soluble except when they're with this silver 1 ion. This is called the mercury 1 ion or the lead 2 ion. So for instance, we can say that the compound lithium chloride would always be aqueous because chloride is always aqueous except with silver, mercury, or lead. And we can also think of it as containing lithium, and so lithium is always soluble, so it should always be aqueous. However, if we had the compound lead 2 chloride, PbCl2, looking here, chlorine, or the chloride ion, is always soluble except with lead 2, mercury 1, or silver 1, and because that fits that exception, this compound is a solid, making it insoluble in water. Something similar down here for sulfates. Sulfates are always soluble except when they're with strontium and barium. So these are group 2A ions. And also sulfates are insoluble when they're with this mercury 1 ion and lead 2. So if you see sulfate with a combination of any of these cations, it would be a solid or an insoluble compound. Now notice that our compounds that are always soluble, or our ions that are always soluble, have those +1 or -1 charges, and things that make them insoluble are often ions that have multiple charges. And so that means that we have higher lattice energies, which makes them insoluble in water. Now down at the bottom portion of the table are ions that form compounds that are mostly insoluble. For instance, carbonate and phosphate, we have a charge of -2 on carbonate and one of -3 on phosphate, so multiple charges, meaning most of these compounds have really high lattice energies. And in fact, carbonates are always insoluble except with the ions that we said are always soluble, specifically those group 1A cations and ammonium. Same with phosphates. Phosphates are always insoluble except with that same subset of cations, the group 1A cations and ammonium. When they're with those, they are aqueous or soluble. Now sulfides and hydroxides are similar. They're always insoluble, but they have different exceptions. One of their exceptions is the group 1A cations and ammonium in both cases, and the other exceptions in both cases are the calcium, strontium, and barium ions. So if we saw calcium sulfide, it would be a soluble compound. However, if we saw maybe iron 2 sulfide, it would be a solid compound, an insoluble compound. Now let's use these solubility rules to figure out if a precipitation reaction will occur. The question is, will a precipitation reaction occur when aqueous solutions of iron 2 nitrate and ammonium carbonate are mixed? Now our two compounds that we're starting with here are FeNO3 and ammonium carbonate, aqueous. These are soluble because we see that they're aqueous. We can also identify the nitrate ion in iron 2 nitrate and the ammonium ion in ammonium carbonate. Nitrate and ammonium are always soluble. In order to predict if a precipitation reaction will occur, we need to be able to predict products. I think that an easy way, or a good way to predict products, is by taking this part of a molecular equation that we're given here and making an ionic equation, meaning we split these aqueous compounds into their ions. So I'm going to split iron 2 nitrate into the iron 2 ion, and the nitrate ion will have 2 nitrate ions. And I'm going to split ammonium carbonate into 2 NH4 plus and CO3 2 minus. Now, in order to predict what new compounds would form, we have to see what can happen. So the iron 2 and nitrate were part of our starting original compound, and the ammonium and carbonate were part of that other compound on the reactant side. To see which products we can form, we have to take the cation from one reactant and combine it with the anion of the other reactant. And then we have to take the anion of the first reactant and combine it with the cation of the second reactant. So we're just switching which ions are with each other. That means that our products that can form, in this case, I'm going to write them as they would be written in the molecular equation. They will be 2 NH4 NO3 and also 1 FeCO3. So we made ammonium nitrate and iron 2 carbonate. Now the next part is to figure out if these are aqueous or solid ions. Thinking back to the solubility rules and remembering what they are, ammonium and nitrate are always soluble. So here, when they're together, they would certainly be soluble or an aqueous compound. Thinking back to where we saw carbonate, carbonates are always insoluble. There are exceptions to their solubility rules, namely the group 1A cations and ammonium. Iron does not fit that exception, and so we will have a solid or an insoluble iron 2 carbonate. And so yes, a precipitation reaction will occur. The precipitate is iron 2 carbonate. Because it's that solid that forms. And we also have spectator ions in this reaction. The spectator ions are those ions that form the aqueous product. Particularly here, we would find that our spectator ions are ammonium and nitrate. So any of the ions that we see that are always soluble are going to be our spectator ions. Let's do one more question. Here we have, will a precipitation reaction occur when aqueous solutions of sodium carbonate and lithium acetate are mixed? Again, we see our two aqueous compounds. Compounds with sodium are always soluble. Compounds with lithium are always soluble, and also with acetate are always soluble. So let's write our ionic compounds written as their formula units. Let's write them as their ions, so as they would be written when they dissociate in water. We will have 2 Na plus ions, and we'll have carbonate. These are both aqueous. We will also have the lithium ion, and we'll have acetate, which is CH3CO2 minus. Now, in order to figure out what new products can form, we will recombine our ions. So the positive ion of our first compound goes with the negative ion of our second compound, and the negative ion of our first compound goes with the positive ion of our second compound. And therefore, the products that we form, which I'm going to write as they would be a part of the molecular equation, the products we form are, let's see, we have to form NaCH3CO2, sodium acetate, and we have to form Li2CO3. In order for this to be balanced, I'm writing it as a continuation of this. We have Na2CO3 plus LiCH3CO2. This is aqueous, this is aqueous. We would need 2 sodium acetates, we need 2 lithium acetate, and we should be balanced now. Now we have to figure out if we formed a solid, and let's think about our solubility rules. We saw at the top here, when we went through why these two were aqueous, it was because compounds with sodium, lithium, and acetate are always soluble. Well, 3 of our 4 ions are always soluble. There are no exceptions to their solubility, and so when recombining them, all compounds have at least 1 ion that's always soluble. Here, on our product side, we have aqueous sodium acetate, so it's going to be aqueous. And we also have lithium carbonate. Compounds with lithium are always soluble, or always aqueous. And so because we have 4 aqueous ionic compounds, this is something that is said to have no reaction. Because if you write the ionic equation and the net ionic equation, you'll find that all of the ions are spectator ions. They would be the same on both sides of the equation. And therefore, by doing this reaction, you'll see that no change actually occurs.